2, Investigating Playdoh Circuits by Sam Pendrick, Heather Sales, and Emily Schloff.
The purpose of this experiment was to determine the resistance of a homemade Playdoh resistor. Resistance refers to the degree to which the current is impeded. Current refers to the flow of charge over a region. Voltage refers to the electric potential difference between 2 points. Ohm's law relates all three variables and states that voltage is directly proportional to the product of current and resistance.
Resistance is dependent on both the resistivity of the material as well as the length and cross-sectional area of the resistor. A formula that relates all four of these variables is R equals rho times L divided by A. In our pre-lab experiment, we used cylindrical Playdoh resistors of known lengths and radii, and we were able to measure current and voltage differences across these resistors. Using Ohm's law, we determined the resistance of the Playdoh. Afterwards, we used the above resistance with the known measurements of the Playdoh resistors to find the resistivity. After averaging all these values, we determined that rho is about 0.294 ohm meters for Playdoh. We had to keep several circuit rules in mind when designing our circuit. There are two ways circuit elements can be arranged. The first is in series or in a loop. In series, elements will split voltage, but the current will stay the same. When elements are in parallel, however, a junction is formed that creates a second path for the current to travel along. Therefore, current varies in parallel resistors while voltage is held constant. It is important to note that current travels along the path of least resistance, so junctions with greater resistance overall will experience a smaller current. There are a few more requirements that we also had to consider. The light bulb required between 2 and 3 volts and no more than 20 milliamps in order to light up. The fan required at least 300 milliamps of current in order to spin. Our challenge was to find the resistance value of the Playdoh that would satisfy all of these conditions.
Our circuit diagram contained 4 batteries, which supplied 6 volts total, the light bulb and the Playdoh resistor, which were in series with each other, and the fan, which was parallel to the light bulb and the Playdoh resistor.
The following is a powerbox representation of our circuit diagram. It displays how current and voltage are split between different elements of the circuit. To explain, since the bulb and the Playdoh resistor were placed in series with each other, the voltage is split between these elements, but since these elements were placed in parallel with the fan, current is split between those elements.
This is our setup, which shows our ice cream cone shaped resistor and the fan and the bulb working together at the same time. Our resistor is broken up into 3 simpler shapes, a cone and 2 spheres, to help us calculate resistance of the total shape. This is data collected for voltage at several different spots in our circuit. This is data collected for current at several different locations in our circuit.
In order to calculate the resistance of our homemade Playdoh resistor, it was necessary to find the cross-sectional surface area of each of the 3-dimensional shapes in our resistor. What complicated this calculation a bit is that our homemade resistor is made of a cone and 2 spheres, which do not have uniform cross-sectional surface areas along their lengths. So this required us to take the average cross-sectional surface areas for each of the components of our resistor, and this occurred when the radius was halved. And since the cross-sections of cones and spheres are circles, the cross-sectional surface area is equal to pi times radius squared. For each of the components of our homemade resistor, we calculated the ratio of the length to the average cross-sectional surface area. We added these together, and then we multiplied by the rho value found in the pre-lab to calculate the total resistance of our homemade Playdoh resistor. We then calculated resistance using an alternative method, Ohm's law. To do this, we used our measured values of current and voltage difference across the Playdoh resistor.
Because Playdoh is not a perfect conductor, it will have some electrical resistance. We made a resistor out of Playdoh that would provide enough resistance for the batteries to power the light and the fan at the same time. For the circuit to work, the current through the light bulb had to be minimized, while the current through the fan had to be maximized. The combined resistance of the light bulb and Playdoh resistor is greater than that of the fan, so a smaller current will pass through this loop, including the bulb. For the fan and the bulb to operate at the same time, the Playdoh resistor had to be in series with the bulb and in parallel with the fan. The resistance of our Playdoh resistor was found to be 49.4 ohms. Since the two ways of calculating resistance gave very similar values for resistance, we can conclude our approximation of resistance is fairly accurate for the Playdoh resistor.
This experiment had several limitations. For example, the estimated resistance of the Playdoh could have deviated from the actual resistance because of the colors of the Playdoh, hardening of the material, and the functionality of the solder beads as time passed. Also, the measurements of the cone and the spheres are limited by the instrument that was used, which is a ruler. The components of the Playdoh resistor are also not perfect cones or spheres, so it's likely that the measurements we took are not accurate. And the metal portion of the wires or ammeter probes could have touched the table while the measurements were taken, and this would have influenced current and voltage readings. And lastly, the multimeter is limited to 2 decimal places.